Okay, this is going to be the fourth video, integration by U-sub. Okay, this is going to be part 4, and as promised, I'm going to go ahead and start with a second way of doing the one that we ended with the last time. Okay, now, do we happen to remember those Pythagorean identities? We should, okay? And what happens here is we should remember that tangent squared x plus 1 is equal to secant squared x. Okay? So let's see whether we actually can change the form here, because I know that tangent squared x is equal to secant squared x minus 1. Okay? Well, if I do that, if I take this into account, I can actually change that into secant squared x minus 1. There will still be a tangent left over, and of course a secant squared dx. Let's go ahead and get secant to the fourth x times tangent x minus secant squared x times tangent x, and we wind up getting that. Okay, we have a two-term one. Now, of course, I didn't say that this was easier. I was simply proving that you actually could do it another way. Well, now, but see, tangent is not exactly a derivative of anything. But if we further break this apart, we know that secant cubed x, and I'm going to actually break this into two separate integrals, secant times secant x tangent x dx minus secant x and then secant x tangent x dx. That winds up being u cubed du minus u du. And so let's go ahead and just take that cubed and pop it out here. Okay, so that winds up being 1/4 secant to the fourth x minus 1/2 secant squared x plus c. How is that equivalent to the answer that I got the last time? Because remember, the last time I got 1/4 tangent to the fourth x plus c. Well, it has everything to do with the identity and the fact that when you change, okay, you have basically a monomial to a binomial, but those actually are equivalent, and both of those are certainly ways of actually accomplishing that integral. Okay, now enough for the trig ID fun. And I've basically included that since I know that you're not keeping up with your trig IDs the way that you should be, so I want to remind them. I want to remind you of them as often as I can. So I have x root 4 minus x dx. Now when we have a radical in the integrand, my default should be u is equal to the radicand. And then I have du is equal to negative dx. And then I have done this before, so I know that x is equal to 4 minus u by back substitution, and therefore I recognize the fact that this is 4 minus u to the 1/2, and then negative du. Now, of course, that negative can be used to turn that around as I'm distributing. And I'm going to wind up getting u to the 3/2 minus 4u to the 1/2 du. Okay? From here, it winds up being rather simple. You're just sort of undoing the power rule, right? So that's going to be divided by 3/2, so multiply by 2/3 times 4 is, of course, 8/3. And from here, you just plug that binomial radicand back in. And here's the thing, you might be thinking, how in the world does that become that that integrand, when I differentiate it. I'm not going to go ahead and do that right now because these videos are short enough or long enough as it is, and we do as many as we do. But if you're curious, go ahead and actually differentiate that, okay? And you will wind up with that integrand right there after everything all cancels and everything works out all nice and neatly. Now let's go ahead and do another one. How about we have x squared plus 4 over x plus 2 dx. Well, that one's a little bit more difficult. How do you suspect we're going to do that? Well, let's play around with it just a little bit. It's obviously not natural log because in order for it to be natural log, the denominator has to be of a higher degree because its numerator has to be the derivative of it if it's a polynomial, right? So basically the derivative of this denominator is 1. It's certainly not x squared plus 4. You can't factor that. That's unfactorable. It's a sum of 2 squares. So let's just play around with it. Let's go ahead and say, okay, well, let's make the denominator equal to u. And let's see what happens when we try and simplify that. Let's, then of course, du is equal to dx. I recognize the fact that x is equal to u minus 2, and therefore x squared is equal to u squared minus 4u plus 4. So this may turn out to be sort of a variety of that back substitution. Well, let's see whether that actually helps us. Okay, so I know if I plug that in, it's going to be u squared minus 4u plus 8 because I have to include the 4 that's already there. So u squared minus 4u plus 8, all of that over u du. So the u substitution didn't actually help me to identify it as a natural log or anything like that. It actually made me able to split it apart by turning a denominator that was not a monomial into a denominator that is a monomial. And now I can basically take that and make that u minus 4 plus 8 over u du. So that's 1/2 u squared minus 4u plus 8 natural log absolute value of u plus c. So I use the u substitution to put it into a form that I actually then can simplify because I transformed the denominator from a binomial into a monomial. Kind of a neat trick, right? And therefore I get 1/2 x plus 2 squared minus 4 times x plus 2 plus 8 natural log absolute value x plus 2 plus c. And there is your integral. Okay. Alrighty. Well, I mean, those back substitution ones wind up looking pretty scary, but as long as you know that move to then solve for x in terms of u, whereas you've designated u in terms of x, you then just plug it in and see what kind of simplification actually occurs. And it actually doesn't wind up being half bad once you've done it a couple of times. So you have x plus 1 over the square root of x minus 1 dx. Okay, well, I have every idea that this is probably going to be another one of those back substitution ones. Not only is the x minus 1 in the denominator, but it's also underneath a radical. That makes it doubly my suspected u value. So let's go ahead and try that out. So if u is equal to x plus 1, then x is equal to u plus 1, and x plus 1 is equal to u plus 2. No matter which one you differentiate, it doesn't really matter. You know du is equal to dx. Well, let's see what that gives us. Okay, that gives us u plus 2 over u to the 1/2 du. Again, I now had something that was a nasty binomial and under a radical in the denominator, and now, according to a polynomial, is a monomial, and therefore by rules of exponents becomes rather easy to simplify. And then from here, of course, I just do it by rules of by undoing the power rule, okay? So we have 2/3 u to the 3/2. If I add 1 to this, it becomes 1/2, so that winds up being 4u to the 1/2 plus c, and then I just have to substitute in the binomial that I designated as u, x minus 1 to the 3/2 plus 4x minus 1 to the 1/2 plus c. Okay, and that winds up being, you know, not a whole lot of fun, but certainly very, very doable. Alrighty. Sorry I keep sniffing, guys. I got a little bit of an allergy problem here. Something's in the air in Aberdeen. Okay, so let's do sine of 2x, cosine of 2x dx. Well, here's the thing. What do I designate as my u and what do I designate as my du? And actually, you can do it either way. You can either do it as u is equal to sine 2x, and therefore du is equal to cosine 2x 2 dx, right? And if I'm going to do it that way, then certainly all I need to do is basically take a 2 and shove it in there, okay? And then of course put the 1/2 out in front, and if I do that, I wind up getting 1/2 u du, which of course winds up being 1/4 u squared plus c, or 1/4 sine squared 2x plus c. But I could have, if I wanted to, have designated it the other way around, right? So I have cosine 2x, sine 2x dx, which of course I'm allowed to do because multiplication is commutative. I'm going to do the same thing, except for I'm going to put a -2 in here and a -1/2 out here, because I know that if I designate my u as cosine 2x, then my du is going to be negative sine 2x times 2 dx. And therefore that's negative 1/2 u du, which becomes negative 1/4 cosine squared 2x plus, or cosine squared, let's do it step by step, u squared plus c, so negative 1/4 cosine squared 2x plus c. There's still actually a third way to do this, okay? The third way to do this is look at the radicand, look at the integral, integrand, okay, sine 2x cosine 2x dx, and I recognize the fact that sine of 2u is equal to 2 sine u cosine u, right? Okay, so if I put 2 right here and a 1/2 out in front, can I, by identity, transform that into that? And then my u is not a trig function, my u is my angle measurement, right? I simply need to plug in a 4 into here, and of course multiply this by 1/4 out in front. That becomes 1/8 sine u du, or negative 1/8 cosine u plus c, or negative 1/8 cosine 4x plus c. Now, are all three of those answers equivalent? The answer is yes, okay? First of all, if I have 1/4 sine squared 2x plus c, which was the first one, right? I know that I can transform that into that using my Pythagorean identities, right? If sine squared plus cosine squared equals 1, then sine squared equals 1 minus cosine squared. Okay, well that just winds up being 1/4 minus 1/4 cosine squared 2x plus c, but then that 1/4 just gets absorbed in the c, because c just stands for constant, like any constant, right? Well, isn't that, doesn't that then transform it into, now of course it's a different c, so I guess we can put c2. That is exactly what we got for the second one, okay? Or how about this? Let's look at the third one. We have negative 1/8 cosine 4x plus c. But I know that cosine 2u can wind up being a number of things, right? Namely, 2 cosine squared u minus 1. It's cosine squared u minus sine squared u. Yeah, so it ends up being 2 cosine squared u minus 1. Okay, well, that means that I can then plug in negative 1/8 2 cosine squared 2x, right, because it's half of that, minus 1 plus c. And then, of course, when you distribute the 1/8, this becomes negative 1/4 cosine squared 2x plus 1/8 plus c. But then, of course, those two can just be combined into yet another c. And we're sort of foreshadowing something that's coming down the pike in Chapter 7, for those of you that are BC students, in terms of using those Pythagorean IDs in order to transform integrands into a usable form such that we actually can perform the integration that we're asked to perform. So I will go ahead and call this video quits at this point. I will go ahead and line up a few more for next time. Those of you who are watching these after the lecture having been given by your teacher are wondering where the definite integrals are. The definite integrals are coming, okay, and we'll get to those here in the next video or two. Bye.